sp2 carbon is going to hybridize so that it can resonate and resonate. So that means, I totally lost count, 6, 7, 8, 9. Oh, whoops, that's not 9, it's 10 because we have an oxygen here that is also capable of resonating. Anything that's left, if it's not a hydrogen, is going to be sp3. Oh, that's one little sad carbon. Done. What about hydrogen? Good question. Hydrogen is just S. It does not hybridize, and your professor will not ask for it. They'll typically say, show all the sp, sp2, or sp3, or they'll give it to you in a multiple choice form, or they'll tell you all the carbon atoms or something like that. Question. Can you explain why nitrogen is sp2? Yes. If a nitrogen or an oxygen atom is near an sp2 carbon, it will hybridize so that it can resonate, because resonance is stability and atoms like to be stable. So if I have nitrogen near something that looks like this, carbon is already oxygen is already sp2 hybridized because it's pi bound, but the nitrogen will take its electrons and move towards the carbon, kicking up these electrons. That'll give you something that looks like this. NH2, the oxygen now has the extra lone pair. The pi bond now sits over here, and guess what? It's sp2 hybridized with a formal charge of +1, a formal charge of -1, which A, doesn't answer your question, and B, leads us into the next topic. What is formal charge? Question. So when you have an atom with a lone pair next to a carbon that is double bound, then don't use the lone pair. I don't understand your question, but if the atom is something like nitrogen or oxygen, it wants to resonate. It wants to attack that partially positive carbon atom. And in order to do that, it has to hybridize, because when it forms a pi bond, it's sp2 hybridized. So it needs to hybridize, and that's why it was sp2. All right, so formal charge is think of it as formal, like official. It's the official charge of an atom. So if you remember in Orgo, in Gen Chem, you learned nitrate, NO3 minus. When you drew it out the molecule, and you didn't put minus on an individual atom, you just put brackets and you put the negative outside. But the formal charge is looking at which specific atom is holding that charge, and sometimes you'll have more charges spread out, and then you just take the net charge, and that's the charge of the overall ion. So let's see. Rachel, you're right. Other Rachel is asking, so just clarifying, you were going to do the major resonance form and then determine hybridization. If you're talking about something like this, then don't even bother. Just take it as the quickest analysis that you can. Nitrogen near an sp2 carbon is sp2. Oxygen near an sp2 carbon is sp2. If you're asked for resonance, then obviously take the time, draw it out, or pick the choice that has the right answer. All right, so formal charge is going to look for the specific atom holding the charge, and the formula that most of your textbooks have is awful, because if you have a quiz on formal charge, fine, you have 5-10 minutes per question, you can take the time. But if you need to find the formal charge in 2 seconds for the purpose of answering a bigger question, like a longer question, you don't have that kind of time. So instead of what is the equation? Let's see if I remember it. It's the number of valence electrons minus, open parentheses, the number of bonding electrons divided by 2 plus lone pairs. Something ridiculous like that, right? I don't like it. I'm going to use the shortcut of should minus has equals formal charge. The number of valence electrons that the atom should have minus the number of electrons directly attached, so what the atom has on it, and that is formal charge. Let's take a look at something simple. If I have hydroxide, everyone knows oxygen is negative, but let's prove it. So here I have my 8 electrons. Oxygen should have 6. What does it have directly attached to itself? 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1, and that's how we get a formal charge of -1. We talked about a carbocation. We said it's carbon with a positive charge. Let's prove it. If we have a carbon bound to 3 methyl groups, then let's prove that this is indeed a carbocation. How many valence electrons should a neutral carbon atom have? Carbon should have 4. Directly attached, I only have 3. 4 minus 3 is positive 1. That's our carbocation. Carbo, carbon, cat, positive, ion, an atom or molecule that lost or gained an electron and now has a charge. Carbo-cation, where cat has a plus in the word. Why do I start with formal charge? Because the next thing I want to look at is Lewis structure. Now there are many, many different ways to draw Lewis structures, and I find that it can potentially get very, very confusing, especially when you have to introduce pi bonds. So what I like to do is follow a very short checklist, and if you can check off every item on the list without changing anything, then you know you're correct and you're good to go. So the checklist is as follows: atoms, octet, electrons, and formal charge. And that's why I started with formal charge, so that we can use it in the checklist. Anyone type in the first ion that comes to mind, polyatomic ion. Before we go into a polyatomic, let's take a look at something simple, BH3, just to show you how to use the checklist. First thing we want to do is start with atoms. For atoms, you want to take the least electronegative atom that is not hydrogen, and that is critical. Whoops, I forgot I had that on my clipboard. All right, so you have the periodic table here. Boron is not on the table that I had you memorize, but I did have it here. It's the exception to the octet rule, only likes 3. Why am I starting with the atom that is least electronegative but not hydrogen? The reason is hydrogen can only have one bond. So if I have a chain and I want to add to it and I want to add to it and I put a hydrogen, I'm stuck. I can't add anything else. So I want to start with the central atom that I can build on. And the least electronegative atom is likely to get attacked by all the more electronegative atoms, and that's why we put that in the center. In this case is boron. We're surrounded by the 3 hydrogen atoms, and that lets us check off the atoms. The next thing I like to do is give everything a full octet. First you want to draw a single bond between the atoms, so that'll give us 2, 4, 6. I'm not going to do 8 because boron is an exception and it's happy as it is, so we'll stop right there. Electrons, boron should have 3. Hydrogen should each have 1 times 3 is 3. 3 plus 3 is 6. 2, 4, 6, we're good to go. And formal charge, never bother with hydrogen. If you have a hydrogen atom on a bond, it should have 1, it has 1, it'll always have 1, unless it's an H-, a hydride, and you're not really going to be asked to find the hydride unless you're given hydrogen that looks like this, which is kind of obvious right there. So if you see hydrogen bound to an atom, it's 1. Ignore it. Boron should have 3. Directly attached, it has 3. Formal charge, 3 minus 3 is 0. We are good to go. All right, questions on the Lewis structure checklist. All right, so the first polyatomic that came in is H3PO4. That's not a polyatomic, but we'll pull the polyatomic out of it. And we'll take H2PO4 minus. We'll use the checklist, atoms, octet, electrons, formal charge. I'll give you a table to peek at. What's the first atom I want to start with? I want to start with the least electronegative atom that is not hydrogen, and so I compare phosphorus to oxygen. Phosphorus is more to the left and lower, so 2 methods of identifying that it's the least electronegative, which gives me a phosphorus in the center. I have 4 oxygen atoms, so I'm going to surround it. Anytime you see hydrogen at the start, put the hydrogen on your outer atoms. Put them on your oxygens, not on your phosphorus. So I'll just randomly put a hydrogen here and a hydrogen here. All my atoms are present. Next, I want to do octets, but first I want to bind everything so we have single bonds between them. And then we want to fill in the electrons. Now I like to go with start with too many and then cut back. So you create an octet, you know what it has to look like, then you can move things around if you need to. So oxygen needs 3 more pairs, 3 pairs, 2 pairs, 2 pairs, and phosphorus looks good. So right now the molecule looks good to go in terms of the octet. But let's see about electrons. Hydrogen should have 1. We have 2 of them, so that's 1 times 2. Phosphorus is under nitrogen, so that should have 5 valence electrons. Oxygen should have 6. 6 times 4 is 24. And then the negative charge is an extra negative, so you do plus 1. So we have 2 plus 5 plus 24 plus 1. If you don't have a calculator with you, then try to look for patterns when you add it. 24 and 6 is 30, plus 2 is 32. We should have 32 electrons. What do we have here? 2, 4, 6. Notice I'm counting them by 2. Always count by 2, and also always look for patterns. If you look at this oxygen, with a bond, it's a total of 8. That means this is also going to be 8 because they're the same. This right here is 8. This right here is 8. So we have 8 times 4, 32. The electrons are all good to go. Check. But now formal charge is going to get a little interesting. Oxygen should have 6 directly attached. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. Don't even do the hydrogen. These two groups are the same, so that means they're both 0. But now, take a look up here. Oxygen should have 6, but we have 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is negative 1. That means this one is also negative 1. How can we have negative 2 if the charge of the molecule is only negative 1? The answer is don't stop. Phosphorus should have 5, but we have 1, 2, 3, 4. So for that one, 5 minus 4 is positive 1. The net charge on this molecule is negative 1, and positive 1. Negative 1 minus 1 is negative 2, plus 1 is negative 1. That means we are good to go. The only thing is, phosphorus is an exception to the octet rule, and you generally want to stay away from separation of charge. If you have a negative near a positive, the negative will try to attack the positive, and you'll get a structure that looks like this. Phosphorus with an OH, another OH, a double bond to the one that attacked, and then if you redo the formal charges, you'll see that phosphorus is now 0. Oxygen is 0. The negative and positive canceled out. But here you have negative 1, and that's the charge of the molecule. Question. So hydrogen is more electronegative than phosphorus? It's not about hydrogen being more or less electronegative. It's about the fact that we ignore hydrogen. Hydrogen is always a filler, so you want the least electronegative atom that is not hydrogen, and that's the one you start with. Question. So both of these structures are acceptable? I believe so. If you ask me what it looks like, I would draw this one, but your professor may want to see both of them. And if you have to draw both, just call this one the major because it has no separation of charge, and this one the minor because it has extra separation of charge. Question. This question goes back to formal charge. What is the difference between formal charge and oxidation state? Okay, I probably should have read that before saying it out loud. I don't want to open a can of worms. Formal charge is the actual charge. Oxidation number is an imaginary charge. Question. The electronegativity moves down the periodic table. It's up and towards the right, not down. So fluorine is your most electronegative atom. And since oxygen is both higher and more to the right when compared to phosphorus, oxygen is more electronegative than phosphorus. Question. So to clarify, we chose phosphorus over oxygen because we chose phosphorus because it is less electronegative based on the electronegativity trend on the periodic table. If this is not a topic you're comfortable with, go back to the videos I assigned earlier, the Orgo Basics, actually the Intro to Orgo series, which is linked on that page, and watch the video on periodic table trends because I actually break it down in detail. Even though it's Gen Chem, you definitely have to know it for Orgo. Question. Because phosphorus is an exception to the octet rule, can I ask why you added the double bond to satisfy the formal charge? Phosphorus has a full octet, but phosphorus is big. It can hold an extra bond, and if that extra bond will take away the positive charge, it's happier. So even though it seems to violate the octet, it's still happier because there are less charges going on. Question, so you're just doing resonance? It's kind of resonance, right? We're resonating those electrons down. I want to show you another tricky one. It's kind of easy, but I want you to see how this checklist works. So the molecule in question, let's take a look at carbon monoxide, and we'll look at atoms, octet, electrons, and formal charge. In this case, the least electronegative atom will be carbon, if you need to see it right there, carbon and oxygen. We put a single bond between them and then complete their octet, so we'll have 1, 2, 3, 4, 5, 6 around each one. But take a look at the electrons. Carbon should have 4. Oxygen should have 6. Total of 10. We have 2, 4, 6, 8, 10, 12, 14. We have 14 electrons. So what do you do if you can't check off the electrons? So here's how you treat this and still follow the rules to make it as simple as possible. Because I know professors will tell you just start throwing bonds out there, and the students will bring me their quizzes and they're missing electrons, octets are violated, formal charge is just off the wall. What you want to do here is ask yourself, what's wrong with this picture? I have 4 too many electrons. How do I get rid of them? 2 at a time. If I take away these 2 electrons, carbon has an incomplete octet, right? If I take away these 2 electrons, oxygen has an incomplete octet, so I can't just take away electrons. But what if I take away these 2 electrons and take away these 2 electrons? I just took away 4. Now, carbon and oxygen are both missing 2, so what if I put a bond between them? They both still have a complete octet, but now I have 2 less electrons. Now I'm at 12. I still have 2 too many though, so I'll do it again. Find 2 atoms that are next to each other, that each have a lone pair, get rid of them. That's -4. Put a pi bond between them, that's +2, and now we're at 10, where we want to be. Right, so the key is to find 2 atoms that are near each other, that each have a lone pair, and just cancel the lone pairs, put a pi bond between them. Now we have carbon and oxygen, each have 1 lone pair, and a triple bond between them. Carbon should have 4, it has 5, 4 minus 5 is -1, so that's negative. Oxygen should have 6 minus 5 is +1, that's +1. +1 minus 1 is 0. Formal charge matches the net charge on the molecule, and there's no way to get rid of the charge, so this is the only way that you can show it. This is chlorate, ClO3 minus. Let's take a look. We have atoms, octet, electrons, formal charge. We'll start with the least electronegative atom, put it in the center. In this case, chlorine and oxygen are actually very close in electronegativity, and your professors will not ask you to judge between one to the left and one down. They're very close. In a situation like this, take the atom that appears in a smaller number and put that in the center. So in this case, we'll have chlorine in the middle, surrounded by 3 oxygen atoms. So, atoms are good. Let's put in some electrons. We have to complete the octet on oxygen, and oxygen again, and chlorine. Okay, so now we have complete octets. What is wrong though? Let's see how the electrons look. Alright, so we have a complete octet on each atom. What about the number of electrons? Chlorine should have 7. Oxygen has 6 times 3, which is 18, plus 1 for the negative charge, which gives me some 14, 26. Okay, so now what? How many do we have? 8, 8, 8. 8 times 3 is 24. 25, 26. We appear to be good to go. Are we good to go? Alright, so they appear to be okay. The electrons are good, but now let's take a look at the formal charge. Oxygen should have 6. Each one has 7. 6 minus 7 is -1. So we have a -1 here, -1 here, -1 here. What's going on? Well, chlorine should have 7. Directly attached, we have 1, 2, 3, 4, 5. 7 minus 5 is +2. chlorine, even though it has a full octet, is very, very unhappy because it has a charge of positive 2. And this highly electronegative atom is not happy with a +2. Question: chlorine can't have 3 bonds, can it? Not only can chlorine have 3, it's going to have 4 in the structure. Remember, chlorine is an exception to the octet rule, and it can have more than a complete octet. And certain atoms, when you have electronegative atoms bound to each other, are going to get a positive oxidation number, a positive formal charge, and they're going to have something weird like chlorine, which is about to get a 4th bond. Let's redraw this in a little bit of a simpler version. We have chlorine bound to 3 oxygen atoms. Each one has 3 lone pairs with a negative charge, and chlorine has a +2 and a lone pair. So what are we going to do? For every negative and positive, we're going to do one cancellation. Negative attacks, so now we form a pi bond. Negative cancels one of the positives, and the same thing happens here. Negative cancels the second positive. So chlorine is going to have, in this case, a double bound oxygen, a double bound oxygen, and a single bound oxygen. Oxygen is now neutral, neutral. Chlorine is now neutral, but notice it has 5 bonds, and the oxygen here is left with a negative charge. But what if instead of forming pi bonds with the 2 oxygens on top, I chose to use the lower oxygen? So for example, what if I put a green pi bond here and a purple pi bond here? Is that allowed? And then I'll make this one the one with the negative charge. But what if instead I chose to have a pi bond here, a pi bond here, and then this one has 3 lone pairs and a negative charge? Is that allowed? And the answer again is yes. So everyone who said yes, you're absolutely correct. What happens in reality is the electrons are constantly moving back and forth, and resonance is absolutely correct. This is considered resonance. The blue electrons will move down to form a pi bond. Chlorine is now at the point where it has way too many bonds, so it's going to kick out one of its lone pairs. It's going to kick out one of its pi bonds to form a lone pair, and then you show a double-headed arrow from what it was to what it forms. And we can do the same thing again. We can now show the purple electrons going back towards chlorine, the green electrons collapsing down, and what does that look like? First thing you want to do is the double-headed arrow. Ask yourself what didn't change. This one. What did change? Well, we now have 2 lone pairs and a pi bond, and this is no longer a pi bond, it's now 3, whoops, that's not 3 lone pairs, and the negative charge moved down. If you want to prove to yourself that the negative charge moved, go ahead and do a formal charge on each of them. So if they're all allowed, then you put brackets around it to show resonance. My question to you is, which one is the one you'll see in nature? What is the correct structure for chloride if I just showed 3 here? None of them are more or less major or minor. Well, technically we can say that this is the major structure and any of its resonance, and this right here is minor. And the answer is all 3, or rather the in-between of the 3. What happens is the electrons are moving through this back and forth so fast that it's really a blur. But if you were to freeze it in time, you might get this version, or this version, or this version. But in reality, what's happening is going here, 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 back and forth, with a partial negative on each of the oxygen atoms because they're each taking turns holding that negative charge. So if you're asked about this, remember, the resonance hybrid is what you really have, but on paper you can't show it, so you show all the contributing resonance structures. When it comes to drawing resonance, SB2 is correct, but when it comes to drawing resonance, what you want to look for is what makes the most sense. So resonance obviously is pushing arrows, so you want to see what makes sense. You always start your arrow where the electrons are. So the tail is where the electrons are, and the head is where the electrons go. Never do it backwards. Never start an arrow at a hydrogen atom and make the hydrogen attack something. Hydrogen is a proton. Protons don't move. So it's always about where the electrons are and where they want to go. Electrons are negative, so ideally you want to look for negative. Negative would be literally a negative charge. So for example, if you have a resonance structure where you have an oxygen atom with 3 lone pairs and a negative and a pi bond here, ideally you want to start your resonance where the oxygen, I don't know why I did that so small, where the negative oxygen collapses down and these electrons then get pushed. If you don't have a negative, the next thing you want to look for is lone pairs. Look for lone pairs. So for example, a fun one to draw is this, and I'm not going to draw all the resonance structures, but you guys are welcome to try it. If you have a molecule like phenol, there are no negative charges, but we have lone pair on oxygen. That can start resonance, which will cascade into the ring, and then you would show all the different resonance structures. Look for the lone pairs. And then if you don't have a negative and you don't have a lone pair, then you want to look at pi bonds. So for example, if you have something ridiculous like this, make it a nice conjugated system. This will be a nice chain reaction. These electrons will move, these electrons will move, and then these electrons will move. Question, but oxygen has lone pairs. It has to be lone pairs that can move. These electrons, the lone pairs, can't move. Why can't they move? Because if they try to go down, you're going to form a 5th bond to carbon and you have nothing to kick out. Actually, that reminds me of another trick. If you can remember this, you're likely going to save yourself a lot of trouble. Never, ever, ever resonate onto an sp3. Carbon, oxygen, nitrogen. So many students try this and it doesn't work. You absolutely cannot resonate it. If you have something that looks like this, and I'm just trying to see what I can make up here, it looks like that. The logic is to want to do this and do this, but the problem is that is sp3. That means no resonance. If you try to resonate there, you're making a 5th bond. If you're making a 5th bond here, that's fine because you kick out the pi bond and that means you're back down to 4. But if you try to resonate onto sp3, you can't because there's no way to kick out that 5th bond. We have a question on the ClO3 and it looks like we forgot the lone pairs. So yes, chlorine still has its lone pair of electron. That never moved. So let's not forget that.